And today I'm going to talk a little bit about my laboratory. And we are really doing some things that are very exciting, I believe. 10 years ago, it was taboo to drink during pregnancy. Women knew it was wrong, they didn't do it, doctors admonished against it, but nowadays things have changed. I think a lot of it has to do with the explosion of social media. People are getting their information about what to do and not do during pregnancy and in parenting from sites like Twitter and Facebook, etc. And right now, we're going through kind of a big change culturally, where free will is so important for our behaviors, and we want to be able to do whatever we want to be able to do when we can and we will. And what we're finding is that more women, particularly educated women, are engaging in drinking behaviors, particularly wine. This is wine. It's actually a grain, but it's a grain on wine, during pregnancy. And so what we're seeing is an increased number of children who have a fetal alcohol spectrum disorder. And this is a term that's an umbrella term that involves all the way from a very mild effect of that prenatal exposure to ethanol from maternal drinking during pregnancy, all the way to something called fetal alcohol syndrome, which is a much more severe effect. So in my laboratory, we're really twofold. We're interested in finding out what are the mechanisms by which ethanol damages the developing baby. But we're also interested in targeting mothers and trying to let them know the truth. So what's really cool, in my opinion, about our work is that we're not just engaging in basic science, but we're taking that information and applying it and trying to do some public outreach and really educate the public, particularly moms and moms-to-be, that really is a very dangerous, risky behavior and not worth it. In our laboratory, we have done some very exciting studies in prenatal ethanol exposure, where we work in mouse model to expose the developing embryo to ethanol. And we've made some really exciting discoveries in that first generation animal, the animal who is exposed. We found that the way that their brain develops, particularly the connections or the network that integrates regions within the neocortex, that this circuit is actually disrupted from prenatal ethanol exposure. And we know from my previous work, when I was a postdoc, that gene expression during early cortical patterning is what regulates these intraneocortical connections and that circuit, and that's how we get this very complex brain that allows us to do lots of sophisticated behaviors. If you drink ethanol, it seems that the gene expression is altered, and then thus, after that, the connections are mistargeted and creates an abnormal network that really creates problems in behavior for the animal. Now, let me show you some data in our across 2 generations, because what we were interested in is not just how is this affecting the baby who is exposed, but with all this new onset of epigenetic research, we began to believe that perhaps our change in gene expression that we've observed in the exposed animal might be caused by an epigenetic modification, and that if it is, this could be heritable, right? And this is something that's heretical and very new. No one would ever really naturally think that fetal alcohol syndrome, right, from being exposed in utero, that this would be a heritable condition. That even if your whole life you never drank and went to have children later, that they would be affected by something your mother did. But now we're finding out differently. And I'm going to show you some new data today that actually is unpublished, and this is the first time I've presented it. And it's really very exciting. It's a little bit hard to see with the light. In the normal animal here, you can see that this is a slice through prefrontal cortex in a mouse. And this is a newborn mouse whose mother, a newborn control mouse. And you can see from making an injection in the caudal cortex, there is no labeling of red cells in the frontal cortex. That's a normal animal. The back of the brain is not connected to the front in the normal animal. However, this group right here is our fetal alcohol exposed animal. So this now is a newborn whose mother drank during the pregnancy. And hard to see, but there are red retrogradely labeled cells in the prefrontal cortex from a visual cortex injection. So this is a very abnormal cortical connection. The visual cortex all the way connected to the very, very rostral pole, which is really like a premotor, prefrontal cortex area. And also, likewise, from a somatosensory injection, which was done in green, we see label far caudal than normal. You can see in the normal control animal here, there's no green label. So we really see a complete disruption of the circuit. Places of the brain are connected to other places that are not supposed to be. So this obviously would cause a lot of difficulty for the development of behaviors. What's really exciting for us is that in the second generation of animals, there are red labeled cells in this rostral location. So this is an animal who was not directly exposed to ethanol, but his father was. So his father was a fetal alcohol father. He grew up his life with no alcohol. He bred with a control female who never had any alcohol. And guess what? Their baby is affected with this disruption of neuronal targeting. Okay? And here we've done some calculations of dye counts. So we can see that there's a significant difference between obviously control and the first generation of ethanol-exposed animals and even the second. Now, in our gene expression data, we see something similar as well. In our control animal, this is expression of RZR beta at the level of the somatosensory cortex. RZR beta is positive in somatosensory cortex here. This is in the control animal. You can see that the high-level expression stops here, and you have a fairly thick developing lamina. And here in our prenatal exposed animal, we see this extension, this increase of RZR beta expression, and it is extended rostrally. And also we start to see a compression of label within the developing lamina. And what's really exciting that we just recently discovered was the similar pattern in our F2 generation. So again, we see a disrupted gene expression pattern which results in a disrupted cortical network in the non-exposed second generation. It was really, really very new and exciting work. And I skipped one, sorry. We quantified, my graduate student Charles Abbott quantified the gene expression across a couple of different probes here for ID2, EPHA7, and RZR beta. You can see here this first little one is the control. In the F2, we see a reduction of gene expression, and in F1 and F2, we see a huge increase in gene expression for the frontal cortex. In the caudal cortex, we see something similar, where we see increased expression in both. Likewise, this is a big effect of RZR beta, large degree of increased gene expression in both the F1 and the F2 generation. So this is basically a quantification using qPCR of the previous slide where I showed the qualitative in situ hybridization. Now, you might ask again, okay, so we know that ethanol is changing gene expression in the first and even the second generation, but what might be the mechanism? And that's where we started to look at epigenetic modification. And here we looked at global 5-methylcytosine and hydroxymethylcytosine levels in control, first generation and second generation animals. And what's really very interesting is when you see decreased methylations here in the caudal cortex, let's say, typically decreased methylation, you're going to get increased gene expression. So we see epigenetic changes that have happened as a result of the ethanol exposure in the first generation and also in the second generation of animals. So this is really starting to give us this idea that fetal alcohol syndrome, or the spectrum disorder, actually is most likely a heritable feature. And it's something that then can be passed from generation to generation. This is very, very important because if you think about it, it makes it even more relevant and more reason to not drink during pregnancy. We see that even in the second generation, we're getting these epigenetic changes. And you might ask, as we have, well, this is all interesting molecular biology, but what about behavior? And one thing really I think super cool about my laboratory is that we combine molecular biology with neuroanatomy and with behavior. So we try to cast a wide brushstroke to try to understand how this developing system works. And our behavior assays, we have a few assays here in the F1 and the F2 and control mice. A couple of these are measures of motor development and others are of anxiety. So for example, for anxiety, we can look at the latency to leave center. So this is on a test called a SUOP test, where the animal's placed in the middle of the bar. If they're really anxious, they're going to freeze. That's what rodents do. And you can see that from the control, comparatively, we have statistical differences between the control in F1 and between the control in F2. So this was really an interesting effect. We actually saw really highly increased anxiety in the F2 mouse. Also, we saw some increased anxiety as a measure of rearing and grooming between the control and F2, but this effect seemed to go away a little bit on the F2 animals. For motor malfunction, we see increased missteps, so they're slipping off the bar, both of them, F1 and F2 compared to controls, and also increased numbers of falls per segment crossed. And when we look at the rotor rod, it actually comes out very nicely as expected, right? We see the learning performance across trials in the blue, the control animal. The F1 has fairly poor performance of learning in this motor task across trials. And we see our F2 kind of being somewhere in the middle. So together, our data really demonstrate that there are epigenetic modifications that happen from the ethanol exposure and that these are transgenerational, and that they are also causing anatomical changes in the brain and read out in behavior. So we hope that this doesn't only provide very good information to science, right, about the basic biology of how ethanol works in developing brain, but we also want to reach out, and we have with our past work, to the community to try to educate the community that despite what you may read on Facebook, drinking ethanol in pregnancy is not safe, and we have very significant data in a mammalian system to demonstrate that. And lastly, I just want to show a quick picture of my laboratory. We have some people here still. Olga Kazanian, Sarah Santiago, who recently graduated with her PhD. Hani Ashawa was my first PhD graduate. And we have, here's Lily, who's now in Peter's lab. And Andrew and Charles, who has really been the major spearhead for the work that I showed you today. And thank you. And I don't have time